Information. All right, now let us take a look at the controversy of the day. So this is not a historical experimental review. It's something that came up in a discussion, and I wanted to look at it into it a little bit. So some of this we'll be learning at the same time. There is an experiment. So that disclaimer aside, I will give you. I will be learning this at the same time you do in terms of what are the techniques that are being employed. Although I do have a bit of background that can be useful at an appropriate time. So there's an experiment at CERN called the Aegis Experiment, right here. Okay, and the question that they are asking is, if you have a gravitational field, so like here's the surface of the Earth, and you have hydrogen, so here's a hydrogen atom, and then you have antihydrogen, here's an antihydrogen atom. Do these things fall in different directions? Does antihydrogen have negative matter? Or maybe do they fall at different rates? Because this is made out of antimatter. That's a bar above this, by the way. So this is antimatter, antihydrogen, and this is regular hydrogen. That says hydrogen. There's a G in there somewhere, right? There you go, hydrogen. And so the question is, does regular hydrogen fall at a different rate than antihydrogen? Or do they fall in opposite directions? Does hydrogen and antihydrogen couple to gravity the same way? The standard model of physics says that yes, they couple the same to gravity. But there is an experiment at CERN that's asking this very question. They can produce antihydrogen, and they can make these measurements, like are they falling at different rates in the beam that they produce. Now, there are a few reasons or a few things about this to keep in mind. One, it's not just protons and antiprotons that we're talking about. The issue is that if you have a proton, let's say that you have if you want to look at what's the interaction strength between a proton electrically and a proton gravitationally, you get an enormous difference. So if you were to take, like, what's the force of gravity between two protons, you're looking at big G, the mass of the proton times the mass of another proton, so that's the mass of the proton squared, divided by their separation squared. So you can just say, put in a meter, you have big G in there, you get some number out. The mass of the proton in kilograms, so this is like, I guess we can do this. G is 6 times 10 to the minus 11. If you do 1 meter, then that's 1 meter squared in the denominator. The mass of the proton is 10 to the minus 20, I think it's 10 to the minus 27 kilograms, 10 to the minus 27 kilograms squared. That's 10 to the minus 11. We'll say that this is 10 to the minus 10, right? We'll round this up. So it's 1 times 10 to the minus 10. So big G is 10 to the minus 10. You got 1 meter squared. You've got two protons that you bring close together. That's going to be 10 to the minus 64. 10 to the minus 64 newtons. 10 to the minus 64 newtons is not particularly strong, right? That's a small number. Now, if we look at the electrical interaction between two protons, so we're looking here at the force, electric force is going to be K. So it's 1 over 4 pi epsilon naught, but K is the other abbreviation. And then we're going to do the charge of the proton times the charge of the proton squared, divided by 1 meter squared again. So that's going to be, okay, K is 9 times 10 to the 9. That is 10 to the 10. Right, K is 1 over 4 pi epsilon naught, which is 9 times 10 to the 9, which is 10 to the 10. Okay, and then R squared is also going to be 1 in this case. And then the charge on, whoops, this is not squared. It's that one quantity. Okay, the charge on the electron is 10 to the minus something or other coulombs. How many coulombs is that? Proton electric charge, is it 10 to the minus 16? Well, plus 1 doesn't help, right? I want the actual thing in coulomb. 10 to the minus 19 coulombs. So electric charge is 10 to the minus 19 coulombs. All right, so this is 10 to the minus 19 coulombs squared, and then we multiply all these things out. That's 10 to the 10. This is 10 to the minus 19 squared is 10 to the minus 38, and so this is 10 to the minus 28 newtons. Did I do that right? 19, that's 40, and then subtract 10. Okay, 10 minus 28. All right, so that's still a small number. Still a small number. However, the ratio of the gravitational force between two protons and the electric force between neutrons is the ratio of these two things. And so if we want to do electrical force to magnetic force, or electrical force to gravitational force to see what the difference is, that would be I'll do that up here in this corner because that's the only space I have left. And I don't want to erase all the numbers. That would be 10 to the minus 28 divided by 10 to the minus 64, which is an enormously large number, right? That's basically 30, and that's 36. 10 to the 36. So the strength of the electromagnetic force is 10 to the 36. That's a 1 with 36 zeros after it. That's a very big number. That's more than all of the numbers that we have at our disposal in terms of, like, I mean, this number is gigantic. The age of the universe in seconds is, what's the age of the universe in seconds? 10 to the 10 times 10 to the, is like 10 to the 18 seconds. So the age of the universe is like 10 to the 18 seconds. This is, for every age of the universe, it's another age of the universe. For every second in the age of the universe, it's another age of the universe. That's how big this number is. This number is enormously big. So the moral of the story being that the electrical force is significantly stronger than the gravitational force. And we can see this ourselves, right? The electrical force that we can produce in our bodies as we jump up into the air, we saute into the air using the electrostatic repulsion that we can generate between our feet and the ground, is capable of overcoming the gravitational pull of an entire planet. The entire planet is pulling us down, and we are able to escape, at least momentarily, its clutches by jumping up into the air with our own legs. And so that is pretty impressive at the relative strength of the electromagnetic force to the gravitational force. So the gravitational force is very weak. So when you produce just antiprotons, if you just have a beam of antiprotons or regular protons, if they're bare, they have electric charge. Right, so if you just have a beam of protons like this, it's got electric charge, and so you can have no stray electric fields, like no stray electric fields to the tune of 10 to the, what was it, 36, to the tune of 10 to the minus 36. Okay, if you want to measure the gravity on a proton, gravitational pull on a proton, you need to eliminate all electric fields down to this level, which you can't even measure. Right, that's so small that you can't even measure it. And so what options do you have? Well, the only option that you have is to put an electron with it. So you have a hydrogen atom, a neutral hydrogen atom, and at that point it's electrically neutral, and you don't have to worry about this anymore. You don't have to worry about stray electric fields from the wall, like a small piece of something that's stuck in the walls of your chamber or whatever. Or electromagnetic signals coming from the radio station that's nearby, or the air traffic control tower, whatever it might be. And so if you want to do antihydrogen, which would be P bar E plus, so you have antihydrogen. If you want to compare the gravitational effects on these two things, then it needs to be hydrogen and antihydrogen, not just protons and antiprotons. Because if it's just protons and antiprotons, you have to eliminate this systematic effect, which is non-trivial. Okay, so that is what they're doing here. Here is the Aegis experiment. Is scientific goal of the Antihydrogen Experiment Gravity Interferometry Spectroscopy, Aegis, is the direct measurement of the Earth's gravitational acceleration, little g, on antihydrogen, to see if antihydrogen falls differently. Hey, Paul Person, how's it going? Falls differently from regular hydrogen under the influence of gravity. It's a collaboration of physicists from all over Europe. The first phase of the experiment will use antiprotons from the antiproton decelerator together with a pulse laser excited positronium atoms obtained by shooting positrons into this thing. Because the vertical deflection due to gravity is expected to be minute, as opposed to minute, this is minute. Even though it's spelled the same way, it is minute, not minute. Small, few microns. The beam of anti-atoms will need to pass through a device that can superpose a pattern with a structure of the same size in microns. Such an instrument, for example, is a moire deflectometer. So it looks like they're going to send in a beam of particles. They're going to have an interferometer that gets these particles to interfere with each other. That's why it has this interferometry part. And then they can, because it's an interferometer, you're able to see very small changes in the deflection that you get from them. Okay, so from this pattern, we can thus measure how much antihydrogen atoms of different velocities during the drop during their horizontal flight, because they're going in a beam relative to the beams of light, which do not drop on our scale, and thus determine the strength of the gravitational force between the Earth and the antihydrogen atoms. Anyways, this is the experiment they have, is to check out the effect of Earth's gravity on antimatter and compare it to Earth's gravity on regular matter. Does antimatter fall with the same acceleration as matter? So the principality of universal freefall, or the weak equivalence principle, states that all bodies fall with the same acceleration independent of mass and composition. That was Einstein's, well, it's Einstein, but it also goes back to Galileo dropping the two different things from whatever tower he dropped them from, whether or not it was the tower in Pisa, that things accelerate towards the Earth at the same rate, independent of their composition. The weak equivalence principle has been tested with very high precision for matter, but never directly for antimatter. And so this is where the point of contention is going to arise, this never directly for antimatter. So buckle in. The principal goal of Aegis experiment is to test the weak equivalence principle with antihydrogen atoms at CERN, using antiproton decelerator to provide antiprotons and some kind of sodium source to supply us with anti-electrons. I guess this is a radioactive source that produces anti-electrons, and then they merge these things together to form. That's kind of interesting. How do you make antihydrogen when you don't have a source of anti-electrons? And the answer is we make the source of anti-electrons by probably having some I suspect this is a beta emitter, a beta plus emitter, to supply the anti-electrons, and then you just blast these things through it, and then it will capture the electrons as they go. Interesting. That's my guess as to what's going on. Otherwise, why is sodium, right? Why not use something else? Which we combine to form antihydrogen atom. Direct tests with charged particles are hopeless given what we saw, the extreme weakness of gravity relative to other forces. Our method requires forming many atoms of antihydrogen at once, giving them a horizontal velocity kick to get them flying in one direction, and finally measuring a tiny vertical shift due to gravity, all of which requires a bunch of state-of-the-art stuff. All right. So, and it's got this international, interdisciplinary, and young team from all over the world. And the question then becomes, is this even necessary? Okay, so this is an experiment that's working directly with antimatter and comparing it directly with matter in the same experimental apparatus. Now, here is where, as this was being developed as an experiment, so this is like H bar Aegis with a G bar over it to see, how does antimatter, so that it's clever. There are a number of experiments that test the weak equivalence principle, right? Testing the weak equivalence principle, which is what they said right here. The universality of free fall, or the weak equivalence principle, that's the thing that says that objects, regardless of their composition, it's energy that it's accelerated, and so it doesn't matter what it's made out of, as long as it's got energy, and that energy could be in the form of mc squared, it will fall at the same rate under the influence of gravity towards the Earth. And it's not like the weak equivalence principle isn't just towards the Earth, it's towards any object of any composition. Any two objects of any two compositions will fall towards each other regardless, the same way, regardless of what they're made out of. And you can change any one of them as long as it has the same total energy, or the same, in this case the mass is the only thing that's important, they will fall at the same rate. Okay, so that's the weak equivalence principle. All right, enter the torsion pendulums. So we've talked a little bit about torsion pendulums already, where you have some object where you're detecting the strength of gravity between an oscillating pendulum or a balance if it's just stationary and you're moving the mass around it. But one object that's suspended by a fiber, and then you have surrounding mass, and you're using that surrounding mass to couple to the pendulum, the thing that you have hanging there, in order to detect the interaction of the gravitational interaction between the object that you have. So if I draw a picture of this, between the object that you have, which is in the form of, so you have some kind of pendulum like this, and you'll have some mass over here that's your source mass, and you're looking at the gravitational attraction between these objects, and maybe you have a second mass over here to preserve the symmetry, and it will cause this fiber. It's a very thin fiber, maybe like 10 to 100 microns across. I don't know. It depends on the nature of the experiment that you're running, like the mass of the pendulum that you're hanging. So this is a very thin fiber, so it's got a very weak spring constant, and so small forces can cause it to twist. And fortunately, gravity is a small force. So then you're looking at what is the gravitational attraction between these two things, and how much does it cause the pendulum to then twist so that these things can be more aligned with the masses. The masses of the pendulum can be more aligned with the masses of your source. And then you can do a bunch of fancy shaping of the different parts of this, like you have a different kind of pendulum, you shape it in a particular way, you place the masses in a particular location or in a particular configuration in order to look for different behaviors than what you might expect. So that's a torsion pendulum. It's extremely sensitive. Like torsion pendula and interferometers are like the most sensitive kinds of instruments that we can make. Okay, so there are a number of torsion experiments that have been done specifically testing the weak equivalence principle dating back to Eötvös in 18 something or other. So let us take a look at what these experimentalists have to say about it. So there's two groups that did torsion pendulum experiments looking at gravity at the University of Washington. I was part of one of the groups. There is another group. That other group is called the Eötvös group. So let me scroll up to the top of this particular presentation. This was a presentation that was given at Simon Fraser University by Eric Adelberger at the University of Washington. Eric Adelberger is an exceptionally good experimentalist, and Todd Wagner was apparently a graduate student, and this is what they're looking at. All right, so in particular, they're looking at the weak and strong equivalence principle tests. So Todd Wagner. All right. Things, ways to test gravity. Watch things fall down. Watch things fall sideways. This is Eötvös. This is not so obvious. Currently, the most sensitive tests are done here. And these are the kinds of things so these are the kinds of experiments that people are running, is these Eötvös experiments. And they named their group. They don't have their group up here, the name of the group up here, but they named their group EOTWASH, EOTWASH, because it's a play off of this, and it's at Washington, the University of Washington, and so it's a fancy, clever thing. All right, let's see. So the weak equivalence principle tests, they have these things. Here's what they have. They have, these torsion pendula. They're designed in a particular way. This is kind of a ugly drawing, but it's what they have. And so he describes some of the background of this thing, and you come down here quite a ways, and you look at, suppose we have no preconceptions about the nature of equivalence principle violation and want unbiased tests. It requires sensitivity to a wide range of length scales, so it doesn't, like something that violates the equivalence principle, some force that's acting on your pendulum. Oh, I guess I should back up a little bit. He has this thing here where yeah, that's not really that important. So the way that this is interpreted is if there's a violation of the equivalence principle, the way that we would describe it now is that it's not actually an effect with gravity, or perhaps it is, but it's a more general form of gravity that includes new particles and new interactions. And so that is, you're looking for violations from the way that Newton predicts gravity should behave, or the way that Einstein predicts gravity should behave. All right, so you need a wide range of length scales because you don't know if these new interactions are, thank you for that raid, Dr. WD40, appreciate that very much. 102 people. Thank you for stopping by, everybody. So we're looking at the effect of whether matter and antimatter fall at the same rate. There's an experiment at CERN, the European Particle Accelerator, where they're looking at this. And in this case, we're looking at what other groups have to say about this who have also done experiments looking at weak equivalence principle, which is the measuring the rate at which things fall under the influence of gravity. Okay, so you need to be sensitive to a wide range of length scales because if some new force is mediated by a particle, if the particle is massless, then its force is infinite. It will have a force that extends forever like gravity does. But if the particle that has it contributes to this force has some mass, then it will have a length scale. And you need to be able to measure both the strength of its coupling and the length scale over which it interacts. So for example, the strong nuclear force interacts only on length scales the size of the nucleus. And so we don't feel the strong nuclear force once you get outside of the nucleus. The electrons don't feel the strong nuclear force. It's only the particles in the nucleus that feel it because the strong nuclear force doesn't make it outside of the nucleus. All right. So you need to be sensitive to a wide range of length scales, and you need to be sensitive to a wide range of possible charges, whether it's something that couples the way that gravity does, the way that gravity we think it does, in terms of everything has a positive charge, or whether it's something like an electromagnetic field, where you have both positive and negative charges, right? So when you have positive and negative charges, you have a vector interaction, or you could have like intermediate vector boson, like the weak nuclear force, where you have three different colors, three different charges, red, green, and blue. So in this case, you need sensitivity to a wide range of possible charges, meaning things, a wide range of possible quantum numbers that this new force would couple to, whether that be electric charge is a quantum number, color, that's a quantum number as well, or something else. So these are the things that you want to build. So torsion pendulum experiments look like this. This is a weak equivalence principle torsion pendulum experiments from 2012. A 20 micron diameter tungsten fiber. You can barely see it there because of how amazing it is, amazingly thin it is. So you don't want to drop these things because 20 microns, the whole idea is to get this to like 60% of the tensile strength. So any jostling will break the fiber. So 20 micron diameter tungsten fiber, you want it really thin because you want very, very weak forces to be able to influence how much this thing is twisted. You have mirrors on the surface for measuring the pendulum twist. The mirrors in this case are probably just copper that are polished. Symmetrical design suppresses false effects from gravity gradients and so forth. If you move a chair in the wrong place, this makes it so that it's easier to mitigate the fact that the chair might have twisted slightly on, it's one of these office chairs that swivels like this. And so by having these things, you can eliminate some of those effects. All right, so it hangs, it's got this thing. This is what the array looks like. It's about 10 centimeters across. It's got these different trays. These are masses where they can place these steel balls. This is so the trays here have a variety of different holes in them that you can place the masses that you want to test. This is measuring gravity gradiometer. So this is trying to see if, maybe there's a water tank in the building next door, and that water tank emits some gravitational field, and you want to eliminate that gravitational field by adjusting where you place, some maybe countervailing, pretend, for example, that you have in a building next door, you have a big water tank, and you want to counteract the effect of that water tank, and so you have a brick, maybe a brick of lead. Let me draw a picture of this. So let's suppose that you have, here's your room, here's the room next door, there's a big water tank against the wall, here's your experiment set up, and it's very sensitive to gravity, and so it feels the effect of this water tank. Well, you need to measure the effect of the water tank, and so you need to design a pendulum that can measure that presence, and then you want to trim it away. So you trim it away by, I know the mass of the water tank, I can measure its distance, I can measure its gravitational effect. I'm going to put a brick on the floor right here. And this brick, even though it's less massive, it's closer, and then you can cancel out those effects. So what you'll do is you will measure the gravity gradients. Maybe there's a bird's nest up here, and the bird's nest creates a gravitational field, and that's going to affect things. And so you're going to counteract that bird's nest by putting, a piece of, I don't know, pick your favorite substance, chewing gum. You put a piece of chewing gum on the floor to counteract the effect of the bird's nest. And so you want to measure these gravity gradients, and that's what this pendulum is designed to do. And it looks as though, I haven't actually worked with this specific pendulum, but it looks as though they've made these holes here so that you can move these things around. And you can say, all right, I want to measure a gradient that comes in a particular direction. And so it's set up like this. You can see the direction that the gradient that you can measure. It's sensitive to things in the upper right and in the lower left. And then you twist it around and see how it samples things in different places. And then say you want to measure a different gravity gradient, one that has a different shape, that maybe you have two objects on opposite sides of you, and you want to counteract those ones by putting things in between them. And so you could rearrange, this is a configuration. So, here's the 4-to-1 configuration. It's exactly what I was saying. So then you can rearrange the location of these balls, these ball bearings on these things to measure different gravity gradients. And so you can see in this configuration, they have 4 on the top, 4 in the, the next one down, and then the 4 on the opposite side over here, and then at the bottom. So they have 2 sets on one side, 2 sets on the other. But if they want to do the Q41 configuration, which is a way of calculating where all these things are located, then they'll put 4 up here, and then there's 4 on the next one on the opposite side. So these 4 over here are switched to the opposite side, and they can just place them there. And then it goes back to the one and then back to the other. So they can measure these different gravity gradients by rearranging where these extra masses are and then measuring the gravitational field. So it's not that gravity is destroyed in this case, it's that it's counteracted. So gravity always adds. And so in this case, you have a gravitational force that's been added by the neighboring experiment that has a laser cooling system, and they need to have a system of water that they can pump through their device. And so you need to counteract it by adding an equivalent force on the opposite side. You can't eliminate it. but you can counteract it by balancing it with some trim masses. Okay, so this is a pendulum they have to measure these gravity gradients, just for experimental interest. This shows you kind of how they can design their source masses. Here's like a hillside. So this is like the index experiment that I was part of briefly, used a hillside as a local mass. They also have a hillside next to their laboratory because it's on the University of Washington campus, right where the dormitories are. And there's kind of it's not a cliff, but it's a fairly steep hillside next to the laboratory where they run these things. They also have stacks of lead bricks. The experiment that I was on had kind of stainless steel Lego type things that would stick together to do that. Anyway, so they measure these things to test for the equivalence principle. And they look for differences in acceleration based upon the masses that they have in their pendulum. So in this case, here they have a variety of different test bodies. So the shapes of these different pieces, let me see if I can zoom in a little bit to make it even more awesomer. The shape of these different pieces and the materials that they're using to make them, they're designed to be the same. So the shape of this is supposed to be the same as the shape of all of these other things. They're not exactly the same. They're close to the same, but they're not exactly the same. Then they coat it. It looks like they've coated it with copper. The reason you want to coat it with copper is because, as we've seen, if you have electric charges, stray electric charges, you're already 34 orders of magnitude stronger than the gravitational force. So you want to coat it with a conducting surface, and it looks like they coat it with copper. I can't confirm that. That way, if there is some electric charge that gets stuck on something, the copper will conduct it away up along the fiber and out of the system. So it's a way of not building up static electric charges on the surface of your pendulum. This is important. The one that I worked on was made out of glass, and so we coated ours in gold specifically so that if there was an electric charge that developed on the surface, as soon as it hit the surface, it would be conducted away from the pendulum, because all it takes is one spare electron on the surface of this thing, and you're kind of, well, that's a systematic effect that you have to deal with. All right, so notice that these things are made out of different materials. They have beryllium, they have titanium, and they have aluminum. And that way what they can do is they can put everything together, demonstrate that if everything is made out of the same substance, that they get a particular behavior, that it behaves the way gravity does. And then they can replace some of them with the same shaped object, which has the same gravitational interaction, except that it's made out of a different substance. And in particular, you want it to be made out of a substance that has a very different number of protons and neutrons in it. And so beryllium and titanium are very, very different. If we look at the periodic table, ptable.com. So beryllium is what, number 7 in the periodic table, and titanium is number something or other. So in this case, you wouldn't want to use a superconductor. Well, okay, the experiment that we were on did use some low energy, some cryogenic stuff. What is going on? Here we go. Is that going to show up? No. It's not showing the whole thing. Oh, there we go. That's better. So in the case of these experiments, I think that theirs was running at room temperature. There are experiments that operate cryogenically to eliminate some of the thermal noise. But superconducting things, that becomes expensive if you need to be a superconductor at like 4 Kelvin. Okay. So beryllium, number 4. So beryllium number 4, which means that it's got basically 4 protons and 5 neutrons. And then you've got titanium, which is wolfram, tungsten. Wait, no, this is tungsten. I meant titanium. It's titanium, right? Titanium. Titanium is 52. Titanium. 52. And so, or 22. 22. So that is 22 protons and it looks like 24 or 26. 22 protons and 26 neutrons. And so you have a difference in the relative number of protons and neutrons. That's the important thing. So the density of these two different metals are roughly the same, and that they're chosen specifically so that they're roughly the same. That way the objects that you make are going to be the same size. However, even though they're the same size, they have different numbers of protons and neutrons in them. And those different numbers of protons and neutrons means that in one case, the mass is made out of mostly equal numbers of protons and neutrons, and the other one is more neutron rich. So even though they're the same mass, one of them has more neutrons per kilogram than the other one does. So if you have some force that couples differently to protons and neutrons, it would show up in the fact that you have a different number of protons and neutrons in these different things. And then you have aluminum as another one in there. So aluminum's here at 13, which is basically halfway between the two, also has a similar density. And so they chose these things because they have a similar density, so they can make them similar in size, but they have different numbers of protons and neutrons in the nucleus, and therefore you get different compositions between these things when it comes to other quantum numbers. So all chemicals are made out of protons, neutrons, and electrons. For every proton that there is, there's going to be another electron. If not, then your experiment's already broken. So all of these things are going to have equal numbers of protons and electrons, and so that doesn't give you any difference in like how would you distinguish these two substances. The only thing that you have to play with is the number of neutrons in the system. And so there you go. So they have different compositions, especially different compositions in terms of neutrons that they measure. All right. So then they make these measurements. How different is the acceleration of protons and neutrons towards the different masses that we've made? And they look at, I don't know what n means. They have the sun, so they're looking at differences between the sun, differences in acceleration between titanium and beryllium and aluminum relative to the sun. This is the galaxy probably right here. The change in differences in acceleration relative to gravity. I'm not sure what W is, and I'm not sure what N is. That's going to be some quantities. W might be, I don't know, the hillside, and N might be the something else. Notice, however, that all of these things, they have these numbers. They measure something that's close to zero, and this is 10 to the minus 15. 10 to the minus 15. That is a tiny, tiny number. The acceleration due to gravity is, big G is 10 meters per second squared. This is 10 to the minus 15 meters per second squared. That is 1 billion, trillion, 1 quadrillionth of the strength of gravity. Those are tiny measurements. But all of these things, even though the number itself is non-zero, the error bars straddle zero. So all of these things are consistent with zero, right? This is 3.1 plus or minus 2.4. So that looks like it could be a little bit different, but you would expect with this many measurements to have a third of them more than 1 sigma away. So I haven't gotten to whether Aegis found anything. I don't think that, so the Aegis experiment that we started this with at CERN, I don't think has results yet. What they did is they passed a technical milestone, is my understanding of what's going on. But I don't know. You'd have to find out. It looks at the Earth, the Sun, like differences in acceleration from the Earth to the Sun and to the dark matter halo in the galaxy. So this is an interesting thing. They made these measurements and compared them to where the location of the center of galaxy is, because there's a lot of dark matter towards the center of the galaxy. And they said, okay, well, let's see if we can get a difference in acceleration between protons and neutrons relative to the dark matter halo of the galaxy. How awesome is that? You build a tabletop experiment, you put it in the laboratory on the side of a hill in Seattle, Washington, and then you constrain the properties of dark matter with that. So I have to admit, that's pretty gnarly. These are the constraints that they get in terms of deviations from regular gravity. All the yellow region has been excluded. And you can see that at large length scales, like towards the galactic center, towards the sun, and so forth, they get fairly good constraints. But at small length scales, so 10 to the minus 2 meters, like 10 millimeters, like 1 centimeter, there the constraints are much, much worse, right? It goes up exponentially there. And those are challenging experiments to make. It's hard to make experiments that are sensitive at really short length scales, because you're getting things really close together and other forces can start to become important. So that is, one must recognize that this is pretty gnarly. These results are pretty gnarly. And wow, the fact that they're doing so much better than lunar laser ranging. So that's when they bounce laser beams off the moon, because contrary to the beliefs of some, we have actually been to the moon. There are retroreflectors on the moon, and we can bounce laser beams off of those reflectors on the moon and probe the weak equivalence principle with those laser beams. Okay, so this is the galactic halo thing, kind of shows how it was done. And this is the important thing. Gravitational properties of antimatter, and this is how it relates to this experiment at CERN that we were talking about. So the torsion pendulum people complained that CERN shouldn't be spending their money doing this antimatter gravity measurement because their experiment's already excluded. And torsion pendulums never get the respect that they deserve. And there's some truth to that. Torsion pendulum experiments don't get the respect that they deserve. And this is at the University of Washington, and that's not Harvard, and therefore, we must be smarter than them. Although it's not Harvard that's proposing to do this other experiment. And so, nevertheless, how do torsion pendulum experiments constrain the properties of antimatter? Now, I should point out, Eric Adelberger is very well respected in the scientific community, but the scientific community that does gravity experiments is not very big, especially torsion pendulum experiments. All right, some people suggest that antimatter could fall up with an acceleration minus g exclamation point. So it's minus g factorial. They propose to test this by dropping antihydrogen. So we've heard this. This is the experiment at CERN. A very difficult and challenging experiment. How plausible is this scenario? Point d'interrogation. If antimatter falls up. So these are some kind of generic complaints that this group has about making this matter-antimatter gravity experiment. And there could be reasonable discussion to be had here. So I'm not going to argue. I don't know what arguments would be made by the other side as it pertains to these things. So I'm not going to speak for them. In this case, I'm just going to advocate for, or I'm going to present the arguments made by the torsion pendulum group. And I don't know what responses they would get. And so to be fair, this is the stuff that I understand a bit better. And so if there are complaints in the other direction, they would show up. That's for the literature to sort out. Okay, anyways, if antimatter falls up, photons are their own antiparticles, and therefore they should not fall. And we know that photons do fall because you get deflection from photons as they go around, as they bend around objects. Like general relativity says that photons are deflected, and general relativity satisfies the weak equivalence principle, and photons are their own antiparticles. So anything that's its own antiparticle should not fall. And yet we see them fall. And then this is the one that's harder to contend with, I think. Well, okay, maybe that one's hard to contend with, but this one I think is more interesting. Nucleons, the mass of the nucleon, so a nucleon is like a proton or a neutron, and what you have in the nucleus is, here's a proton, for example. It's got 3 quarks. It's got a red, a green, and a blue quark, and it has a gluon field that's going around in here. The mass of the quarks is really small. The mass of the quarks in the center of a proton is a small fraction of the mass of the neutron. Most of the mass of the neutron actually comes from the gluon field. It comes from the energy that goes into binding things together. So the binding energy from the strong nuclear force is what gives the nucleus its mass. Most of its mass comes from the binding energy. And that's what they say here. 99% of the mass of the nucleons, the protons and the neutrons, consists of glue and anti-glue particles. Gluon and anti-gluon particles that are swimming around inside the nucleus. And therefore, because electrons don't interact with the strong nuclear force, electrons get their mass directly. Electrons have mass. They are not, as far as we can tell, they are not multi-component particles. And so the nucleons get most of their mass from a gluon-anti-gluon field. So there's some antimatter already in the proton in the form of anti-gluons. The electron just has mass. And so the nucleon should fall with 100 times smaller acceleration than electrons if that antimatter goes upwards, right? So it's 99%. So a tiny fraction of the mass is in the mass of the quarks. The rest of it is in the mass of the gluon field. The gluon field is gluon, anti-gluon combined, and therefore it should have, those two things should repel each other, right? Those two things should fall in opposite directions if antimatter falls at a different rate. The gluons and the anti-gluons should fall in opposite directions, and therefore they cancel each other out to some extent, where the electrons don't have that cancellation. And so if you were to drop an electron and a neutron, the electron would fall under gravity 100 times faster than the nucleon does. And that would show up in those equivalence principle measurements where you have more neutrons relative to electrons. Right, so if you have beryllium that has 5 electrons and you have 5 protons and whatever it was on the periodic table, so you have equal number of protons and electrons, and then you have the neutrons that are added in there, and those nucleons are going to fall at a different rate relative to the number of electrons, and that should show up in these experiments. And so if hydrogen and antihydrogen fall with different accelerations, gravity must have a vector component. Consider an equivalence principle test with hydrogen and antihydrogen. This would have delta z over mu of 2, so that's basically saying like how much different would they accelerate. One of them accelerates up, the other one accelerates down, so delta z, z is the atomic number, over the mass is equal to 2. The beryllium-aluminum weak equivalence test, so beryllium-aluminum is those things that they screw into the sides, has this of 0.0328. So so hydrogen-antihydrogen has a very large difference in this proposed scenario where they have different, they feel a different force of gravity. They would be maximally different from each other. Thank you for that sub, I appreciate that. They'd be maximally different from each other. The beryllium and aluminum is not maximally different from each other, but they are different from each other, and they're different from each other at what, like 2%. So it has 2% of the strength of the difference. Nevertheless, that difference is still there. All right. They see no evidence of this effect, this here, with delta G over G greater than a few parts in 10 to the 13. So the probability right now, the maximum difference you can have between matter and antimatter, according to the torsion pendulum experiments, is a few parts in 10 trillion. Okay, a few parts in 10 trillion. That is a small number. The following plot assumes not only CPT invariance and the impossibility of exact cancellation between V and S interactions. And so these are the constraints that they have. So this is the equivalent constraints that they place on the difference between gravity from hydrogen and gravity from antihydrogen. And what you see is the difference in acceleration that they get relative to the strength of gravity is 10 to the minus 12. And it depends on the length scale, right? Some constraints are stronger than others. So at 100 meters, given the nature of their experiment, this is what they were sensitive to. I don't know, it would be more interesting if they were to extend this down to where it turned over and they no longer had sensitivity. Because this definitely does not extrapolate another 5 orders of magnitude. So at some point, this is going to turn over and go back up. I think. So I would recommend to Eric and his group that they make another plot like this that extends down to smaller length scales. That's where they're testing it with their other experimental apparatus. Nevertheless, certainly at large length scales of the galaxy, that's up here, they're looking at differences that are tiny. So, and this is like for different quantum numbers. So the thing here is for different quantum numbers. In one case, it's the number of protons. So if the quantum numbers that are important is the Z number, like the atomic number, versus any quantum number that's uniquely assigned to the different things. I think that's what this means, this symbol. I haven't read the paper, so I can't say for sure, but this is what, this is the kind of stuff that would be going on in these types of things. So in this case, it's the number of protons. In this case, it's any other charge that a new force would couple to, or that gravity couples to, aside from the number of protons. All right, and so they're getting constraints that are like a part in 10 billion. So there you go. This is the argument from the torsion pendulum experiment about why CERN is to some extent wasting their time doing these experiments, testing whether antihydrogen falls at the same rate as regular hydrogen, is that they've already excluded it to a part in 10 to the 12, and CERN is not going to be able to, well, it's part in 10 to the 12 here, a part in 10 to the 10 at other distances. CERN is not going to be sensitive to this. Like the CERN results are going to be up at like 10 to the minus 3, like 0.1% or 0.2%. That I don't know. But it's not going to be like this. I mean, the torsion pendulum experiments are uniquely capable in measuring small forces. All right, so that is their result. Now, or their argument. They do have a paper. Where is their paper? Here we go. This is the same figure. And this is from Classical and Quantum Gravity in 2012. They talk about implications of the results and how it, plays into this hydrogen-antihydrogen. Using our constraint, we computed the upper bound on the vertical component of delta H bar H over G. So that's the difference in acceleration from hydrogen to antihydrogen relative to the strength of gravity is what that means. The results shown in figure 8 indicate that any anomalous gravitational acceleration must be extremely small. well below the sensitivity of current technology, aside from the torsion pendulum technology. One might object that our assumption is unwarranted because it assumes that antineutrons and neutrons should fall with identical accelerations. Indeed, it is. So we computed the upper bound on this for the values that gave the weakest constraint at each value of lambda, each value of the length scale. The results are also shown in figure 8. So the weakest possible coupling that they can get is shown there. Quantity that would be essentially impossible to measure directly. The results would be essentially the same as hydrogen antihydrogen bounds. Had we plotted the corresponding constraints, a quantity that would be essentially impossible to measure directly, the results would be essentially the same as the hydrogen antihydrogen bounds in figure 8. Now, one of the things that was mentioned, or that's shown here, and that was also mentioned in the website, the CERN website, is that this is the first time, this would be the kind of stuff, whoops, that's not the one that I wanted to bring up. I wanted to bring up this one. That these are done with actual matter and actual antimatter. So I'm not opposed to the idea of, running the experiment twice and making sure that you get the same results. So that's not really the issue. There is a significant difference in cost, however, between this experiment that is not going to be nearly as sensitive, or I doubt very much that it will be as sensitive. That doesn't mean it won't be sensitive. And maybe the interferometry increases their sensitivity to where it can compete with the torsion pendulum. So that's a possibility that I don't know. Because interferometry is the other mechanism to make very precise measurements. So it's conceivable that their interferometry will allow them to get down to the level where the torsion pendula results already are. In which case that would be totally cool. I mean, how awesome would that be? Nevertheless, so they'll run this experiment. My suspicion is that we're going to find that matter and antimatter fall at exactly the same rate, and that will be consistent with the results that were put forward by these torsion pendulum experiments here. It has been argued that the existence of a scalar field could invalidate these arguments. A scalar field would have no effect on this because particles and antiparticles have the same scalar charge. That's the nature of a scalar field. That there's no signed coupling to it. Like some things aren't attracted and other things repelled in a scalar field. That's like temperature, right? Temperature is a scalar field, and everything has everything in the temperature field is coupled to that temperature field, as opposed to like a wind, which has a wind field can have directions that are different, and that would be a vector field instead of a scalar field. Because scalar forces between like particles are attractive, a scalar interaction would tend to cancel a vector force, but this cancellation must be unreasonably. So then it talks about, maybe you can get cancellation between a scalar field and this vector field, this vector interaction that you get from the difference between hydrogen and antihydrogen. Because if hydrogen and antihydrogen interact differently, then it's of necessity a vector interaction. And so they're saying that that would require some fine tuning, and fine tuning always makes physicists uncomfortable. So, anyways, that, gotta admit, is a pretty cool result. It's to one thing, I think that is really cool that with a torsion pendulum experiment, you can measure the gravitational effects of antimatter. If nothing else, that's pretty cool. The ballpark for a CERN experiment costs, that I don't know. I don't know how sensitive, like where they're putting their experiment, like how it fits into the experimental halls that they have, how much infrastructure they had to build to siphon it off. For the G-2 experiment, they're probably, at Fermilab, they're probably looking at $100 million-ish, tens of millions of dollars. Certainly with the big neutrino experiments, you're looking at $100 million. So it's probably smaller than that. They have, they typically won't turn over $20 million to young scientists. So you're probably looking at of order $10 million-ish, maybe for that experiment total in terms of like the total cost. This is just a guess because like I said, I don't really know the scale of those things. The experiment that I did looking for dark energy at Fermilab would be, thank you for that gifted sub, I appreciate that. The experiment that I did at Fermilab that was looking at dark energy, our operating budget, so the budget that we could use to buy equipment was like $30,000, but our costs in terms of how much time was devoted by engineers and technicians and electricity and using the test stand and all that kind of stuff was probably on the order of $1 million. And so this is, I suspect it's going to be similar in scale, probably a fair amount more complex than the one that I did, maybe by an order of magnitude. So that's where I get my answer from. It's just kind of scaling up in terms of what's the size of the collaboration. That would probably tell me what is the size of the collaboration. It doesn't say. I guess I could look this up. It's a pretty big set of universities that are contributing to it. So, 1, 2, 3. You're looking at like 16 universities. So it's definitely at least an order of magnitude more than the one that I did. I had like 3 people. I had Fermilab, Michigan, and that was it basically that went into mine. So this is probably an order of magnitude more expensive, which would put it around $10 million total cost ish, something like that. In this case, it may be a single source for funding, right? If, say, they have one person from each of these places, or maybe 2 people from each of these places, this could be absorbed by CERN, because they're using existing CERN infrastructure for a lot of it. They have to add some stuff, maybe they're contributing different things. I don't know how things are actually structured in the EU, because a lot of these places are EU members, right? Here's Lyon, Warsaw, is that Warsaw? So these are from, that's clearly some kind of French laboratory. So, Italy, France, I don't know what kind of internal infrastructure they have to fund these things at CERN. At Fermilab, I think, when I was at Fermilab, they didn't have much funding internally to do new experiments. You could get some, but they started adopting, I don't know if it's currently there, but they were talking about getting what's called an LDRD, which stands for something. The idea is, and this operates at other national laboratories, the idea is that whenever you build a new experiment, you siphon off a fraction, you basically pay a tax. The Department of Energy pays a tax to the laboratories, even though they run the laboratories, that the laboratory siphons off some money from the grant that goes into running a given experiment. So say you run a $100 million experiment, they'll siphon off a couple % of that, so they'll get $2 million that they can use to do pilot studies and develop new experiments, like smaller scale experiments that could eventually grow into larger experiments. And so I don't know if CERN does that. It's something that's fairly common. I know that other national laboratories do that. I believe that Fermilab does that now, but it didn't at the time that I was there. But they were talking about having this as a way of basically making it possible to do more smaller scale experiments that could, produce gigantic results, but that are otherwise hard to get funding for. Simply because, and certainly timely funding, because if you're going to go competing directly with institutions, you have to compete with other programs that are maybe better established and stuff like that. So, lab-directed R&D, yeah, there you go, LDRD. So, and I think it's really useful having these kinds of things, an LDRD program where you can, have an experiment that maybe costs like $1 million a year or something like that. For some number of years in order to maybe to measure things that you might be uniquely capable of doing at a given moment with the expertise that happens to be there and the other experiments that are running and a window that opens up and the laboratory infrastructure and so forth. Now, I'm not saying one thing or another relative to the strength of this particular program, but the only point here was to showcase the arguments against this program, or basically saying that this has already been done using the torsion pendulum experiments, because they're not widely known. Right? These torsion pendulum experiments are not widely known. It's a relatively small community that does it, even though the scientists are well respected in general. So there you go. That is how to measure, does antimatter fall up? It appears, in my opinion, it's already been demonstrated through these torsion pendulum experiments that antimatter does not actually fall up, that it falls the same as regular matter. Otherwise, it would have shown up in the weak equivalence principle tests. All right, there we go. Any questions?